All right, in this video, I'm going to talk a little bit about the energy in a point particle system because it is a very challenging concept to understand. So let's say you have an extended system, so some object that has some shape to it, and there's some forces which are applied to that object, and it follows some path, right? And sometimes we're interested in all of those interactions, which is, how the object itself deforms and how it rotates and vibrates and so forth. And other times we're not. Other times we're really only interested in the path that the center of mass takes. Maybe that's the only thing we're interested in. And so the way to think about that is to think about this in terms of the center of mass system. So what we do is we take this deformable object and we crush it down to a point which is located at the center of mass. It has to execute the same motion that it did in the real system, right? The center of mass still moves along the same trajectory. And it turns out that if we track the forces that act on that object, so if we continue to draw these things, I'm going to try to draw them as closely as I had before. We place them all at the center of mass and we track the motion of the center of mass. This tracks exactly as we would expect in the real system. Well, that actually stems from this idea that we had in early on, which was that the change in momentum of the center of mass, or of the system itself, is given by all the external forces which act on that system. This is the momentum principle for a multi-particle system. Now that momentum of the system is precisely equal to the total mass of the object times the velocity of the center of mass. And so if we're tracking how this object moves, how its center of mass is moving, this description tells us about that dynamics exactly. It tells us that all we have to consider is what the external forces are, how they act on that center of mass, and we're going to reproduce the exact same trajectory that we would expect. Now, we're not going to get all the details. We're not going to get how the individual parts move and how they vibrate and rotate and so forth, but we're able to track how the object overall, how its bulk motion travels. And so one thing that we might be interested in then is trying to understand the energy associated with that kind of motion. And it turns out a way of thinking about that is to take this momentum principle equation and to integrate that equation over the displacement of the center of mass. And so we'll go ahead and integrate this equation from some initial to some final state. We'll take the dot product of the momentum of the system, the time rate of change of the momentum of the system, and its displacement, and we'll dot that into the external force dotted into its displacement of the center of mass. Now, you can already see something on the right-hand side that probably makes a lot of sense to you. We're integrating external forces on the center of mass over the displacement of the center of mass from some initial to final location. This right here is the work done on the center of mass by those external forces. We basically imagine that all those forces act over the whole displacement, and we can calculate the work that's done. If there's a work on this side, then there must be some sort of change of energy on the left-hand side. This is what the energy principle would suggest to us. And if we play a little bit of game with the mathematics here, what we can find is we'll end up with an integral that is the integral of the mass times the change in the center of mass velocity dotted into the displacement. Now I'm going to play another little game. I'm going to move the dt over here, and the mathematicians hate this, but I'm going to do it anyway because I don't really care what they say. And what we'll find is that we have a time derivative of the center of mass position. Well, that's precisely the velocity of the center of mass. So I will go ahead and get rid of that completely. And what we're going to find is that we're taking the dot product of the center of mass velocity and the infinitesimal center of mass velocity, or the infinitesimal change. So we have an integral here that actually has a kernel or a bit that we can actually integrate. And this might look interesting to you because it's taking the integral from the initial to final state, basically the initial velocity of the center of mass to its final velocity, but we're actually integrating over the velocity of the center of mass. There's a formal derivation in the notes that I don't want to go through in this video, but it turns out that this guy right here is keeping track of how the kinetic energy change of the center of mass It's keeping track of the change in kinetic energy of the center of mass. Because the center of mass has no structure to it, because it's a point particle in our model, this kinetic energy can only be translational. It can only be due to moving from one location to another, not from vibration and rotation. So what we end up with is a very clean and relatively simple expression that tells us we can track the translational kinetic energy of our system if we only consider the work done on the center of mass. This is incredibly useful in situations where you don't have very much information about what's going on. You can figure out what the translational kinetic energy change is going to be and use that to find other types of kinetic energy changes. One of the things that's really worth pointing out here is that the work that's done in this system depends on putting all the forces at the center of mass and allowing them to follow the displacement of the center of mass. So the point of application of all the forces in this system, in this point particle system, are at the center of mass, and these forces act over the whole interval that the center of mass is displacing. This is very different from the real system where individual forces act at different locations and may act over different displacements. So you have to keep track of that when you're actually using the full-blown energy principle, which is that the change in the total energy is equal to the work done by the surroundings. Each individual force that's used here can act over different displacements because of their point of application.